morning and welcome to this next lecture on vibrations of plates and shells. Right at the outset I wanted to make a couple of comments here. If you remember this more complex system that we did a derivation for, I did not mention why this is I0. The mass moment of inertia about the axis, about this axis of the beam, okay, that is m r square by 2 for the disk. Okay. Now we are looking at rotations of this form, rotation of the disk of this form. So that is the disk, then it rotates like this, okay, and the beam deflects. So now the mass moment of inertia about this axis that goes into the board is half of that. That is why it is I0 by 2. So that it is actually m r square by 8. The other thing, as I am on this diagram, I want to mention this spring is attached over here and the related potential energy is here. Okay. So now I will just use this opportunity to mention, if I raise the stiffness of the spring value, spring stiffness value, then this will become a zero displacement node point. It will be a restrained point, it will become a support point. Okay. So this idea will come later and I am just reminding you. Now we looked at the Lagrange multiplier method last time, and I said I will show you or give you some numerical values. So this was the matrix form we got, okay, and I also said it is not a standard eigenvalue problem, but it is solvable. So now I will give you some numbers. The numbers are these, based on the number of terms n, number of terms, that is 2 terms, 3 terms, 4 terms, 5 terms and so on. The first frequency parameter, second frequency parameter, third frequency parameter, fourth frequency parameter. And what is it? This lambda is L times m omega square by E I fourth root. This is mass per unit length. Okay. So those values, if you take 2 terms, it is 4.5270. This is numerics on the Lagrange multiplier method. Okay. So this is what we put a constraint here using a Lagrange multiplier. So first natural frequency, second natural frequency and so forth. If you take 3 terms, you get 3.9308 and 8.6794. If you take 4 terms, you get 3.9285 and 7.1221, and here you get 13.461. If you take 5 terms, you get 3.9266 and 7.0985 and 10.428 and 18.999. And if you proceed, you will start converging on the other value, 7.0686. So this has converged. Okay. Then 10.210 and 13.352. Okay. So that's, if you can try this out and see if you get these values, and this is the form of the function. Okay, the form of the function. Now I should mention that this portion of the Rayleigh-Ritz lectures I am taking from a textbook called the Rayleigh-Ritz method for structural analysis, and authors are S. Ilanco and L. E. Monterrubio. It's a very good book. I am only presenting a small portion of it. Now, some comments about this Rayleigh-Ritz method, or before that, let's do one more problem. Okay, so you can even do static analysis. Okay, for example, if I have again a cantilever beam and I take downward positive, and there is this force that is external, that is acting, okay, x equal to 0, x equal to L. Then for static analysis I set my kinetic energy term to 0. The psi m is set to 0. Okay. Then if I look at the potential energy term, the potential energy term now has E I by L cube, and this was there before also, 2 G1 square plus 6 G1 G2 plus 6 G2 square, and the external energy comes as a minus P G1 plus G2 as it is applied at the end. Okay, one term was G1 x by L whole squared and the other term was G2 x by L whole cube. Okay, so as x is set to L, you get G1 and G2. So this is the energy from the external load. So now if we take del Vm by del G1, then we get 4 E I by L cube G1 plus 6 E I by L cube G2 minus P is 0, and del Vm by del G2 is equal to 6 EI by L cube G1 plus 12 EI by L cube minus P equal to 0. Okay, we solve this. What do we get? We get G1 is equal to P L cube by 2 EI, and G2 is equal to minus P L cube by 6 EI. Okay, and the deflection at F L is just G1 plus G2, G1 plus G2, which is PL cube by 3EI. Okay, can do static analysis. Now, from this book, I make some statements that are nice. The Lagrange multiplier method is of course a useful method. But it is not exactly an eigenvalue problem, and you cannot generalize this. For every constraint you have to make special matrices and solve it. Okay, you have to fill in the elements of the matrix and solve it. That's one thing. Okay, that's Lagrange multiplier. Now, in general, for Rayleigh-Ritz method, you need two terms. You need to have two terms for a single mode. The rule of thumb for each mode. Okay. Then if you have a constraint, each constraint requires one term, each additional constraint. An additional term in the summation. Okay. Then issues, various issues. If the stiffness, becomes big, becomes large. Okay, if stiffness becomes large, then you can have ill conditioned matrices. Ill conditioned matrices. In general. Okay. Also, if you have a large number of terms, if you have a large number of terms, that means your f of x has many terms in it, ai, gi, many terms in it. Sorry, let us gi is the constant, so gi phi I, let us say. Okay, large number of terms, even then convergence can become a problem, convergence problem. Okay, and all these problems are more true if you take the simple polynomials. With simple polynomials, okay, they are quite bad with numerics. Simple polynomial means x plus x square plus x cube, that type of a polynomial. You can normalize, but does not matter. Okay. So, if you take something like this, they are generally not very good for numerics. Okay. So, now suppose we want to do a, just as we did with the Lagrange multiplier method, a clamped and a pinned beam. Clamped and a pinned beam. Okay. As opposed or as different from the Lagrange multiplier method, different from the Lagrange multiplier method. Right in the beginning of the lecture, I showed you the potential energy term, okay, F of I think B by L square, something like that. So if you want to do a clamped pin beam, you can put a large stiffness as the potential energy. This we can raise it, okay. Then it becomes a pin joint or support or restraint pin support, becomes a support, okay. However, as I have been saying in this section, if k is sent to a very large value, then numerics can become a problem, because some elements in the matrices will have very high values, can be a problem. So what is a strategy kind of in terms of choice of admissible functions and how to use restraints or how to implement constraints, okay. So a strategy seems to be that find good admissible functions, for an unrestrained system, unrestrained or unconstrained system. That means for the unconstrained system, these admissible functions are good when you do the numerics. Then further if you need restraints required, implement them. Restraints required, implement using springs or even masses. Yes, masses, springs and masses, okay. What a stiff spring can do, a large mass also can do. If you put a large mass, it will create a restraint over there, okay. So now along these lines, so I am just giving you some general statements that are made in the textbook. I think they are very useful. So okay, although this is not a place where we evaluate the admissible functions, this is at the very basic level where you learn the methods. So but some insights are good to have, okay. So there is this penalty method, okay, penalty method, different from the Lagrange multiplier, okay. Here you implement the restraint using a term like this, which you have already seen. This is the potential energy due to a spring, but in here k is sent to a very high value, okay. Now you can also put a mass over there, you can put a mass over there, okay, half mv square type term where you have a kinetic energy, okay. So that also will do the job. In this case m is sent to infinity, okay. Now as you raise this stiffness, as if you implement it using stiffness, say you implement it using a stiffness, okay. In particular what system I have a cantilever beam, let us say, and I want to put a support at the end, zero displacement support at the end, okay. So now if you do it using a stiffness, okay, you can keep on increasing the stiffness, you can keep increasing the stiffness, and it will approach the support value, okay, clamped supported value, supported natural frequencies. and it will approach from the bottom, from lower value. Suppose this is the actual value, the natural frequency will be approached, suppose this is omega 1, and as I raise my stiffness, the value is approached from below. Okay. Of course, if it is too large, that means k is too large, you can have numerical problems, just remember that. Okay. And the other thing is k requires to be larger for higher modes. For higher modes, you will have higher modes, right? You will have higher modes where, okay, for higher modes, So that's a further numerical problem. Okay. Now, so one thing is that you, as you are raising the stiffness value, you do not know where the convergence is, how far you will go, how far is the natural frequency, or where is it, and how high the k has to be, the k stiffness has to be is unknown. Okay. Now, there is an interesting fact mentioned in the text that you can implement it using a negative stiffness also. That means you can implement it using a minus k by 2 f, you can implement it using that also. Okay. And in this case, the natural frequency is approached from above. It is interesting. Okay. So now you can use both positive and negative values and start bracketing, use positive values and use negative values, and you can start bracketing to get a feel for the error. Okay. Another interesting fact is, of course, that the same constraint at the end or support can be implemented using a mass that whose values go to infinity. Okay. Now here, if you, just as you did here, if you implement it using positive m values, then you approach from above. It is interesting. You approach the constrained or supported beam natural frequencies from above. And if you use a negative mass, you approach from below. Okay. And more interestingly, for higher modes, the mass value required is smaller, unlike the spring. Okay. So this is good for numerics. Okay. Now here the book takes the same example of a clamped supported beam where the support is now implemented using a spring with increasing values of stiffness, and again the lambda values are presented. This lambda is the length times m omega square by EI 1/4. Okay, so let me give you the table from that book. The sign of the stiffness then the value of the stiffness, absolute value of the stiffness, and compared with the Lagrange multiplier method. Okay, so let us say we increment thrice 10 to the power 5, 10 to the power 6 and 10 to the power 7 spring units. Then the number of terms taken is 2. Okay. This is again x by L squared and x by L cubed. Okay. The number of terms taken is 2, and for positive and negative sign you get 4.5263 and 4.5277. You can see that this is higher. This is higher. Okay, it is coming from above. Then when you increase the stiffness, it is 4.5269 and 4.5271. Again, this is higher. Okay. Of course, 2 terms does not give you the accurate value, but within the inaccuracy, this is what is happening. Okay. Then with higher stiffness, you get 4.5270, 4.5270. So you have converged, and the Lagrange multiplier gives the same value, but is not accurate, or rather correct. Okay. Then if you increment the number of terms, increase the number of terms, you take 3 terms. Then for positive and negative values, this Lagrange value has come to 9.308 for, let me just make it for 4 terms, and lastly for 5 terms. The Lagrange now converges to 3.9266, here 3.9285. Okay. And at 5 terms plus and minus, you have 3.9264, 3.9269, 3.9266, 3.9267, and convergence at 3.9266 and 3.9266. Okay, that is the nature of convergence using springs with positive negative values using penalty method. Okay. Now a few statements, rather a few theorems are also presented which are interesting. A few theorems are presented in this text. Okay. One that is interesting is theorem 1. I am taking it more or less verbatim from there. The lowest natural frequency of a system cannot decrease as a result of adding one or more constraints. Okay. Then if the number of constraints is h, the lowest natural frequency, let me natural frequency cannot exceed the h plus 1th natural frequency of the original system. Okay, an interesting theorem. What that means is, if we have omega 1, the original system, and we have implemented h constraints on it, then the new set of natural frequencies and the lowest amongst them is bounded like this, h plus 1. Okay. So, this is interesting. The next one is more relevant, theorem 2, which says the rth natural frequency of the system with h constraints, h is the number of constraints, is bounded by the rth natural frequency and the r plus hth natural frequency of the original system. Okay. So, what is it? This is a rth natural frequency original system, this is r plus hth natural frequency original system, and they bound the new rth natural frequency with h constraints. Okay. So, what does it mean for us in terms of admissible functions? Okay. If you have a original correct mode, original exact mode, okay, and instead of that you substitute an admissible function, that is like implementing a constraint, that is like you have put a constraint, okay, because it is different from this. Now, in terms of continuous functions you can't tell how many constraints is this equal to, but it is a constraint, and therefore what does it say? What it says is that the new natural frequency, okay, let us say the first natural frequency omega tilde 1, okay. The constraint is unknown, but it is what, greater than omega 1, okay. Similarly, the rth fellow omega tilde rth fellow, okay, the admissible function here is greater than the omega r, okay. So, every natural frequency is approached from above, and you implement the Rayleigh-Ritz method. Okay. So, time has run out, so I will stop the lecture here. We will continue in next class.